who have joined us for this webinar. Let us start the session with prayers. Om Saishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. Today, we are honored to have Dr.M.V. Hanumantha sir, who will be addressing all of us on the topic Thin Film Science and Technology Application to Optics. A brief introduction about sir. Dr. Hanumantha sir is currently a research professor in physics at Dayananda Sagar University, Bengaluru. He received dual master's degree, MSc and MTech from IIT Delhi and doctorate degree in physics from IIT Kharagpur after graduate study at University Nebraska, Lincoln, USA. His postdoctoral work was at Center for Materials for Electronic Technology, CMET, Pune, as a thin films and material scientist with significant contribution to indigenously develop thick film resistor paste compositions for HMC electronics. He joined ISRO in the year 1999 and was there till his superannuation. At LEOS ISRO, while working as thin film scientist, Dr. Rao has developed a variety of optical coatings in UV visible and IR for payload optics. He pursued parallel development of optics for science and payload systems of Chandrayaan 1 and 2 and Mars orbiter mission and in realization of other satellite-based geoimaging payload optics. He published about 20 research papers on thin film science and optical fabrication and science instruments. He is a life member of Materials Research Society of India, MRSI, Indian Vacuum Society, IVS, Instrument Society of India, Indian Society for System Engineering and Astronautical Society of India, ASI. He is also a member of Optical Society of India, OSI. He was honored by the ISRO Team Award twice for his contribution to Lyman Alpha Photometer Science Instrument for MOM and 1 meter class space optic development. Thank you, sir. Over to you.
Sri Sairam. Thank you, madam, for your nice introduction. I feel very honored to be present here. Teaching has been my passion, though for some reason I ended up with the ISRO. Okay, that is good. I was able to do some good contribution there. And ultimately, after my recent retirement from ISRO, I thought of continuing my academic career as a professor, and Dayanand Sagar University has given me an opportunity to do that, and I am also thankful to them. So, and when Dr. Krishna Jyoti asked me to deliver this one webinar on this on any of the physics related topics, I was very happy to accept that, and I have chosen this topic of thin film technology for science and technology and its application to optics, because I have been working last 23 years on optical coatings required for space applications. So that is the main topic. But before that, before we actually get into the optical coatings, I just want to highlight the importance of the thin film process technology in the present day technology, in the present day developments that are happening all around within the country as well as overall in the technological world. So that's why I felt that it is an important topic, though thin films has been there for more than 50 years, but the technology has developed tremendously, and it is the backbone of the present day latest microelectronics and optics, photonics, and nanotechnology, whatever we talk about, all the latest terminology. The basis is thin films technology. So I want to introduce this to our students here, so that they will be motivated to take up this course in the future and do well. And there will be definitely many opportunities in the coming years within the country. Earlier, all those, this is supposed to be cutting edge technology at some time. So people used to migrate to outside of once they learn the techniques. But now I think many developments are happening within the country. They'll have a lot of opportunities. So with this introduction, I'll start my presentation. I'll share my screen here. Are you able to see my screen here?
Yes, sir.
Yes, sir.
Is it visible?
Yes, sir.
All okay. Okay. I think I need to. Okay, so I'll start my presentation now. So the topic of the today's topic is that I want to introduce all your students and the faculty is the thin film science and technology and its application to the optics. So already as per the introduction, I have been right now working as a research professor at Dayanand Sagar, and hopefully I'll continue to do that with some more projects and also try to help in this developing the thin film science at this university. So let us come to the actual topic. So what is a thin film? This is the first question everybody will ask. If somebody says I am working in thin films, that is the general question. And people will give different definitions like anything less than 1 micron thin, 1 micron, they'll take it as a standard. It is a thin film, or is a 1,000 angstroms is a thin film, is a 100 nanometers is a thin film, or 10 nanometers is a thin film. That is not the way it is done. And the definition what I feel is appropriate is the way I have written it here: a quasi two-dimensional layer of solid material formed on the substrate surface through vapor phase condensation, diffusion, reaction sometimes, and bonding of atoms and molecules. So through all these processes, from wafer phase to a solid layer is formed. That layer that is formed on a substrate surface, that is called a thin film. And before I start, actually my Guruji's photo is covered here. I think I need to move it down here. So I want to pay my respects to my Guruji, Professor K.L. Chopra ji, who was the former director of IIT Kharagpur, and before that, during my MSc MTech time, he was the head of the thin films laboratory at IIT Delhi. And he's a well-known figure. He's a Padma Shri awardee. And he has been the motivation to many students. He has produced almost 60 PhD students. Many of them are professors at many of the IITs, and many are set up big companies in thin films related areas. So I am very fortunate to work under his guidance and complete my PhD at IIT Kharagpur. So, and he passed away last year. So, in fact, last week we had a remembrance of him. And so he's like a father of thin films within our country, within India. He's like that, people will say. So this lecture is dedicated to him because he wants this thin film technology to be taken up by many people, and we have to spread the importance of this thin film technology within the country and encourage people to take up advanced research in this area. So let's come back to that actual topic. So so this is the way the thin film is made. It has to go, whatever material we want to deposit in the form of a thin film, it has to first get vaporized, or the constants of the material should come in the form of a vapor and then get deposited or adsorbed on a substrate surface, and then it will diffuse, and they come together and react together, bond together, and form a solid. One of the typical examples which my Guruji has every time he gives in any public chair is, this is thin film deposition is something like, suppose on a boiling water vessel, you put a cover for a few seconds and take it out. What do you see? You see condensation of water, small droplets, very fine droplets everywhere. So that is nothing but a condensation of water. It is vaporized and again condensed on a cold surface in the form of droplets. That is what basically happens in the case of a thin film that is done in a vacuum deposition system. So that is one of the good examples. So similarly, for example, the soot coming out from a lamp, if you put your hand, you will see a carbon soot film. It's a film. It is definitely a thin film because the vapor is condensed on a glass and it formed a solid layer, right? So that is the way. So these are some typical examples, but it is not as easy as it is. So the nature of thin film now all of you know the solid, I must have read a little bit of solid state physics and know what are the different types of solids. They are depending on the crystalline nature, depending on the atomic arrangement of the atomic arrangement, the solids can be amorphous, crystalline, and epitaxial. Crystalline, we already know crystal structure, you might have studied, regular arrangement of atoms in a certain lattice form structure. If there is no crystallinity, if there is no regular nature, then it is amorphous, or it is amorphous nature. Basically, atoms don't get sufficient time or energy to arrange themselves in a proper ordered manner. So then it condenses in the form. Before that can happen, if it condenses into a solid, then it remains as amorphous film. In fact, most of the optical applications, the oxide films that we deposit they're all amorphous. And epitaxial is the more like is like crystal growth. Just like you heard crystal growth, solid crystal growth, crystal has to be grown in a very ordered way. In the same form, in the case of crystal, you have a crystalline crystal as a seed, and then you slowly pull the seed, and then the liquid atoms from the liquid condense on one edge of the seed and further grow in the form of crystal. In the similar way, here vapor is getting deposited on a substrate. Now, generally, the substrate should have a matching lattice constant comparable to the film that we want to grow as like a crystal. So if that happens, then with appropriate process conditions, if they are set in a proper way, then the vapor atoms are given sufficient time and energy to arrange themselves in a proper way. Then the lattice constants, everything is matching. Then it will grow like a crystal, layer by layer and all that. So that is but then this crystal is not as perfect as what we see in a crystal that we normally see outside, a bulk crystal. There will be some minor defects. That's why it is they coined a name called epitaxial film. Epi means it is in lattice constant is in matching with the substrate, and then that is maintained as it grows. So epitaxial film, when we say, it is essentially a crystalline, regularly arranged atomically arranged thin film. And that is very much more difficult to make it. That requires very high technology. So the physical properties generally slightly deviate from the bulk material, because suppose the same silicon dioxide is there in the form of a quartz material, crystalline, in the crystalline form. Suppose you deposit the same thing in the form of a film, it will not be, it will be amorphous, the crystalline arrangement won't be proper, but certain properties will be different, because the film atoms in a thin film are conditioned by the deposition conditions. It is they are directed by the deposition conditions. So the atomic arrangement will be constrained because of certain conditions. So that's why the properties, the bulk properties and the thin film properties, there will be small variations, such as refractive index and all, they will be slightly different. But otherwise, most of the chemical nature remains the same. So chemically, the materials are same. Only the certain properties will be different because of the crystalline nature of the variation. So thin films are generally, so they have they will be having some defects, or mostly amorphous, and they will be also stressed, because you suppose we depositing metal on a glass or some other on silicon or some other substrate. If there is no matching of the lattice constant, the atomic arrangement of the film and atomic arrangement of the substrate, they don't match with each other. So there will be strain, a bonding strain will be there. That strain will propagate, and it will be in the form of a stress. It will be there up to certain extent. So, and also there will be different defect nature. I think I need to once again move this. Now, if I can close this. Yeah, I think it's better. Also, the electronic properties also strongly depend on the surface and interface effects. And one more advantage of a thin film is, right now I discussed about a single material. It need not be single material. You can always have, we can engineer the materials. We can engineer a thin film structure. You can design a multi-layer, combination of different materials in a different ways, and then study the properties, which will be totally different from the constant individual materials which we are depositing. So thin film process gives a lot of flexibility in innovatively designing and developing variety of materials which are otherwise not possible. So now I'll come back to the importance of the thin film technology. It is an enabling technology. The present day micro and micro engineering that is happening in MEMS, or the present day nanotechnology, wherever the materials are deposited in the form of a film, all this require, and also whatever is not just making a film. Ultimately, you have to study the properties and use it as for a device. It is maybe a thin film solar cell, it may be a sensor, gas sensor, or it can be some electronic, some other device. It may be a laser diode, whatever it is. So ultimately, the thin film process, it is the enabling processing is enabling technology which will be realized the photonic device or electronic device. So it is a very important. So it imparts functionality to this. And suppose we are doing it, this just a single layer of some material on a surface. Certain surface is corrosive. You want to stop the corrosion. Then one of the ways is put a protective layer on the top that will stop the corrosion. Similarly, we can by depositing hard coatings like titanium nitride and all, we can protect the sharp cutting edges of tools and reduce the wear and tear of cutting tools using certain hard coating materials. And also we can use, and of course in microelectronics, we all know that silver and aluminum, some of these materials, gold, palladium, these are all used for electrical contacts in microelectronics. And these contacts are to be deposited by the thermal evaporation or certain one of the thin film process techniques has to be applied. Only thing is, in the case of electronics, everything is designed. Suppose a particular, then a mask has to be prepared to wherever the contacts are required. As per the design, you have to prepare a mask and then deposit the material so that the contacts are formed directly as per the design. Similarly, in electronics, microelectronics, wherever there's some solid state devices, there may be diffusion issues. Maybe titanium is diffusing into silicon. Some such issues are there, or then we need to put intermediate barrier layers to avoid the diffusion of one element into the other, because that ultimately affects the electronic properties of the device. So in the case of optics, using anti-reflection coatings, and we can improve the optical throughput. This is an essential aspect. Without coatings, without anti-reflection coating, there will be no optics without anti-reflection coatings on the lenses, because each surface will have about 4% of minimum 4% of reflectance, and on the combination is about 8% of reflectance if we don't do ARC, and that will generate ghost images and all. So that will create the problem. So the picture won't be good. So we need to put anti-reflection coatings so that the reflection losses are minimized overall, less than 1%. And then only the transmission is there, and then only the appropriate light throughput will be there and image quality will improve. And also in the case of certain insulating surface, we want a top conducting layer like ITO and Kapton, which is one of the activities we have done, transparent conducting layer on a polymer sheet that improves the electrostatic discharge it avoids. You see, insulating charge surface, it gets charged. Ultimately, after some time, there will be electric discharge. But if there is a conducting layer, it will disperse the charge uniformly over the surface, and that way we can avoid electrostatic discharge. In fact, that is applicable. ITO is applicable to the screens also, all the video screens. That is also coated with ITO, and I think most of the mobile screens are also coated because it is a conductive and as well as transparent. So, and also there are other multi-layered electronic materials can be deposited to generate to the latest photonic devices like solar cells, lasers, and LEDs, and even microwave solid-state devices. Thin film technology is used for all the electrical contacts, and also certain dielectric materials are used as microwave devices, and micro actuators. Actuator means apply certain voltage and it moves. I mean, voltage, by applying voltage, there is a movement of because of the stress variations. There is a movement, so that is why actuation happens. So in those applications, we can, if you are using dielectric thin film microactuators are also there to distort a surface or to correct a surface. So that is also one of the applications. So overall, the thin films technology helps by adding a functional part to a sensor. By it improves the efficiency of a sensor. It facilitates miniaturization. We can do the whole sensor can be miniaturized to very small, and then multiple sensors can be made on a wafer. And as I told you previously, it is actually the whole. Once you have a thin film material coating system, it is only our imagination that what type of film that you want to make. We generally follow the what is already published and try to repeat the things or try to modify those things. But in principle, any combination of uh, metals, insulators, and dielectric can be different combinations. You can imagine, you can design and make a film, a multi-layer film, a combination of film, and study the properties which will have some exciting applications. So that is it. Now here I'm telling the next slide. What are the different ways we deposit a thin film? One is there are two main categories. One is the physical vapor deposition, PVD techniques. Another is chemical vapor deposition. And then thin films from a solution. And the sol gel is a slightly, that is also a solution. It's a semi-solid solution. It's a gel, and that also through that process also thin films can be made. But in the case of sol gel, I think it is, though it is not exactly vapor condensation. In this case, but they are all colloidal. Already the particles are formed in the sol gel as in a colloidal form. Micro nano particles will be there. They are deposited, and then after annealing, the particles combine together to form the film. Okay. Let me come to the first part. The physical vapor deposition means, as I told earlier, basically you have to vaporize the material what we want to deposit by heating it either by thermal means or using a high energy electron gun. High melting point materials have to be vaporized with electron gun, focusing high energy electrons focused onto the material, heating, and then it gets vaporized and that vapor gets deposited everywhere. And there are other ways of basically how to generate vapor. The method is different on the ways and means of generating a vapor, which can once again go and get deposited on a substrate. And also how you impart certain energy to the vapor by ionizing, using a plasma, or by many other methods. So one of the, let us see how basically you have to create an ionized plasma vapor of the material. Plasma will help in ionization will help in better adhesion and overall film growth. So in the earlier thermal and E-beam operation, there is no ionization. In the case of a E-beam, there is a partial ionization because the electrons that are bombarding the material, they interact with the vapor that is already getting deposited. So there will be some very minute, they may catch certain electrons and get ionized. But that is only negatively they will get ionized. But that is not of much use. So whereas to improve the process and to improve better quality films, all these new techniques have come up. See, the very first, if you go through historically, the initial methods were thermal. Then to vaporize the high melting points, there is a electron beam operation. And then the sputtering method also is DC discharge. Basically, you have two plates, cathode and anode. You make one of them as a target, which is basically the cathode. Cathode will be the target. And then the ion put a ionized plasma and accelerate, apply, give energy to the ions, argon. Basically, argon is used because it's a very inert material. So argon ions bombard the target and knock off the material from the surface, and that gets deposited. Once it comes out in the form of a vapor, it gets deposited on the substrate. So that is a simple, you can do the discharge using DC method. DC means you use a simple DC voltage of up to say 500,000 or 1500 volts. That is the typical voltage. And in the case of, but then that's okay for metals. But if you want to deposit insulators or dielectrics, because they are insulators, DC means they slowly the cathode will get discharged. I mean, it will collect the charge and it will not work. So we need to put a RF, oscillating energy, That's why RF. But there also, to further improve the deposition rate, RF sputtering rate is very, very slow. Even DC case also it will be very slow other than metals. So then magnetron, what people thought was you can increase the electron density near the target by putting magnets behind it so that the electrons move around and more ionization of the argon takes place. That way it will bombard. Once the more ions are there, there will be more flux of material can be etched out and which will deposit. And in the same case, if you put some reactive sputtering means you add some oxygen or nitrogen in case to the chamber in addition to the material that you are depositing. Suppose some metal and suppose chromium is evaporated and you put some nitrogen in the chamber, then they both react and chromium nitrate is formed. The reaction takes place on the substrate surface. So chromium nitrate film is formed like that. So that is a reactive process. These are all the further innovations that has come up. And then these first two are there almost 30 years. Then later this ion beam sputtering a method has come up. In this case, the ions instead of giving energy internally or instead of improving the number of ions, what they thought was will give argons sufficient energy to bombard directly. So argon ions are ionized and accelerated with a high energy, and those accelerated argons, they bombard the surface. Then the substrate is etched out by sputtering. The sputtering word is used very often is nothing but knocking off the argon ions bombardment, removal of atoms through argon ion or inert gas ion bombardment. It is basically a momentum transfer process. So that is a physical sputtering. So there are other techniques like ion plating and stirred arc. These are all used for hard coatings, titanium nitrate type of coatings. In this case also basically some energy processes, certain methods and techniques are there to impart energy to the depositing atoms, either by ionizing them and further accelerating them towards the substrate. Some techniques are developed. So that's why the names are slightly different. Ion plating and stirred arc is nothing but a electric arc discharge. Basically, we instead of RF power and DC power, see earlier in the case of DC sputtering, arcing is an issue. But somebody innovatively thought that why not, if while arcing, certain material gets vaporized, right? When there is electric discharge, arcing is taking place. What is actually happening? Some material is getting eroded on the electrode. So that method can be used to remove the material from a target, which will in the form of a vapor, and that vapor can get deposited, and so that is a arc deposition. And vapor plasma can also be, once the lasers are developed, high power lasers are developed, people thought that okay, we can vaporize the material using a laser, high power laser, pulse laser, and use the pulse laser to continuously to vaporize the material. And in this, the main advantage of a laser ablation is it is instantaneous and a very quick transfer of energy and vaporization. So it is whatever the target constants, particularly multi-component targets, there are different elements are present at a time, and all the elements, the stoichiometry has to be maintained. Similar ratio of elements has to be maintained on the film. In that case, laser ablation is a good method because all that as a solid, as a whole, it gets vaporized and gets deposited. And if at all any ratios are there, we can also add some extra element, whichever is coming short in the film. In case of, for example, in the case of a physical sputtering, the sputtering yields are different for different materials, elements. So that's why for a multi-component, if you want to do multi-component sputtering, there's a stoichiometry issues are there. Now, of course, there are methods of controlling it and achieving the required composition. I don't want to get into it. Okay. And as I told you earlier, the crystal, if you want a thin film crystal in ports, that is epitaxial film, then molecular beam epitaxy, this is the method. I have shown you one picture here. This is a molecular beam epitaxy. And a single crystal layer by layer formation will happen only under certain very specified controlled conditions. We'll discuss that later. Okay, that is the technique. And most of the latest device like laser diodes and LEDs, they are all made with the MBE technique. And this is one of the very important critical technologies which is not available within the country, except a few places in a few R&D labs. We don't have this type of MBE system. Only a few IITs are having it. Okay. So that is, but ultimately this is the technology that is required for all. Also, there is also another one that is coming up later, the atomic layer deposition. The present day hot deposition technique everybody wants to do is atomic layer deposition. That will come to the, is a part of a chemical vapor deposition. Okay, the difference between physical vapor and chemical vapor is, in the case of physical vapor, already the solid, the material that we want to deposit, it is there in the form of a solid. We are vaporizing it and again depositing. Where in the case of a chemical vapor deposition, the constants of the material film that you want to deposit, the elemental things, they are introduced into the chamber in the form of a chemical vapor. It may be some kind of a organometallic material, or in the vaporized form it comes. Like for example, silicon, maybe silicon tetrachloride or some other silicon silane gas or something. In the gaseous form, silicon is entering, and hydrogen is entering in the form, carbon is entering in the form of a methane or like that. So in the constants are entering into the chamber in the form of a vapor, chemical vapor. And this chemical vapor, when it condenses on the substrate, both types of vapors, and substrate should be able to impart enough energy to these chemicals so that they decompose, and the constant atoms, they react with each other and form a compound. So here in this case, the substrate temperature should be very high, maybe 1000 degrees or 800 degrees like that. So that it can give enough energy to the molecules to decompose, and so that the constant element, the gaseous part will go away, and the silicon or whatever the other materials, carbon, or it can be some other combination also. Aluminum oxide, suppose aluminum hydroxide is introduced, and water vapor is there. They both react on the surface, form aluminum oxide like that. So that is one of the techniques. And in this case also, instead of simply putting very high temperature substrate, and it has to be a metal only, or some other high temperature holding substrate only. We cannot put a deposit on a glass, for example. CVD coating on a glass is not possible because we cannot heat it to high temperatures. But it is possible on a metal surface. So, and hot filament means is basically creating a hot tungsten wire filament will be there when the gas is coming, and this filament is put very close to the substrate. When the gas molecules come in contact with the filament, that heat is transferred, the decomposition of the gas happens, and then and there itself the reaction, the material is formed and gets deposited on the substrate. So these are different ways of doing the same thing. So there are different ways by you can impart energy instead of just heat energy from the substrate. You can impart energy by the other means. You can use a plasma. You can generate a plasma environment so that the ions, the gaseous molecules, their decomposition happens much faster because of some charge particle bombardment, or because of the charged nature of the environment. And the decomposition may happen at a lower temperatures, or it will increase. Basically, the reaction rate will improve if you use a plasma enhanced CVD. Atomic layer deposition, I'll come to that later. It is a layer by layer deposition. It is a very unique technique. I myself do not have much practical experience on this. But it basically, first one particular type of chemical is introduced. It will form a thin layer, monolayer, and then the substrate is heated so that constant element from that chemical is a single monolayer of that element is formed. And then the second constant is further introduced in the next round. That also one uniform monolayer will form on top of that, and each atom from the first layer and the second layer, they react with each other and form the compound. So like that in cycles, it will happen in cycles. The beauty of this process is it happens layer by layer. So that's why this can We can make epitaxial films just like MBE. Here also multi-layer films are possible. Okay, chemical bath deposition. These are all much simpler, easier techniques. You supersaturated. Suppose you supersaturated solution is there. We all know that a supersaturated salt. If you put a salt particle in that, it will immediately crystallize the whole solution. In a similar way, somewhat similar way, you put we put a substrate, dip it in a supersaturated solution of certain material like cadmium sulfide selenide or zinc sulfide selenide, these type of materials. And slowly, once they find certain nucleation centers on the top of the substrate, glass substrate, then slowly some nuclei will form because of the supersaturation, the condensation. And also we can slightly cool it also. Once the supersaturation increases, there is a tendency to form particles and crystals. And instead of forming here and there, it will form, they will find a place on the substrate, glass substrate or whatever substrate that is dipped in the bath. So the film is formed in a slow fashion on the substrate that is dipped in the chemical bath. Spray pyrolysis means the same, it is similar to somewhat like CVD. It is basically a CVD process only in this case. Only thing is, instead of introducing like a gas, the spray is a solution. The solution is atomized and sprayed onto the hot substrate. So basically, by the time the solution hits the substrate, it is in a very misty form. Means very like a mist of this. And then once it comes into contact that surface, again there also the solution atoms, molecules, they decompose and then reaction takes place. So that is also one nice technique. This is also basically essentially from solution to thin film, but intermediately, just before the solid is formed, it turns into a vapor and then reaction takes place and then the solid is formed. Electrochemical discharge, this is also another standard known method of like gold plating and all, we all know. We can plate the gold, and nickel plating, gold plating. These are all the techniques that are used, but there also by appropriate control of the processings, we can achieve a variety of devices can be made and done. Okay, I think I have to go a little fast. I'm trying to explain too much. Okay, other applications, like I already mentioned, these are for some of the examples I'm showing here. These are the cutting tools used in mechanical manufacturing factories. And these are the RF devices. And on one side, you can see the optical coatings of a filter. And this is a vertical cavity surface emitting laser. These are all this is a very high-tech device, VCSCL. There's a very big demand for this type of devices in the near future, because lasers are going to be used, mini lasers are going to be used in electric vehicles, automation, and all that, and many other applications are there. But right now we don't have the technology. And these are the flexible solar cells here on thin film solar cells. And now we can they can deposit like a blanket. You can have a blanket of solar cells and you can spread it and get energy out of that. And their efficiencies are now very much improving and meeting the requirements of, or they're challenging the silicon solar cells. Anyway, right now in my presentation, I'm not going to go into any of these, only optical things only I will be focusing. So, okay, this I can skip it. Vacuum is essential for all PVD coatings, because by generating high vacuum conditions, you can vapor pressure gets reduced, so you can vaporize the material at a lower temperature. And we have to eliminate atmospheric contaminants. In all thin film processing, contamination is a major issue, particularly in microelectronics and optics. Not in the case of wear resistant coating, that is not so critical, but particularly in these electronics and optics cases, we need to do the processing under very clean room conditions. We need to eliminate dust. We need to wear clean room and clothes and all that. We have to follow all the rules of the maintaining a clean room conditions, and also maintain the substrate also should be very pure. Otherwise, there will be issues in terms of quality of the film and coating. So contamination removal, and to perform process under controlled conditions, we need to see Anything, see, any material, if you have heat it to very high temperatures, it will vaporize and it will come out. But ultimately, we need to deposit a very controlled film with the known properties and all that. So all that to have to process the control the process also, vacuum is essential. So how to generate vacuum? Vacuum technology itself is a big subject. Maybe some other time somebody will explain to you what is the vacuum technology, vacuum chambers, how to generate vacuum, different methods, and how to control it. So I'm giving just a few examples here. This is a rotary pump vacuum. Sorry, rotary vacuum pump. This is required to get a 10 to the power of -2 millibar. And to have an idea, our atmosphere is 1000 millibar. We can call it atmospheric pressure is 1000 millibar. Okay. So, and when we evacuate a chamber by pumping out the air inside, this particular rotary vacuum can bring it down to 10 to the power of -3 millibar, means one millionth of a time atmosphere. So it will come down to that. But we need to do the actual vacuum processing, we need to go to 10 to the power of -6 millibar, which is so that is the type of a vacuum that is required. To achieve that, there are different methods are there. There is another diffusion, oil diffusion pump I have not shown here. That is much cheaper. But these are the other technologies like turbomolecular pump. Turbomolecular pump is nothing but an exhaust fan. Exhaust fan, it throws away the air through outside. This is also doing the same thing. It is throwing away the air inside the chamber to outside. But the thing is, it's a high-tech machine. There are certain how it is doing and how efficiently it is doing. That is what is important. So, and we don't have this technology here. And the other one is the cryo pump. In the case of a cryo pump, basically it is some cooled chamber will be there inside in the chamber, which is cooled down to almost liquid nitrogen and further down. In fact, down to liquid helium it won't reach, but down to 10 degree Kelvin. Down to 10 degree Kelvin. You understand, no? Liquid helium is 4 degree Kelvin. But helium is used for bringing it down to 10 degree Kelvin, certain chamber. So once it is cooled, then the air around it will get condensed in that area. Once it is condensed, then there is a diffusion. Whatever the chamber atmosphere air is there, whatever air constituents like argon, nitrogen, water vapor, or carbon dioxide, all these atmospheric gases, they all get attracted or diffuse or move towards the cold areas, which is the coldest area in this whole chamber is that small area within the cryo pump. So everything comes and gets condensed in the form of a solid. What I mean is, it's essentially a solid only. Or it will get condensed in that small area which is cooled down to 10 degree Kelvin. And and it has to run continuously and maintain that temperature so that this vapor stays there till our process is completed. Otherwise, what will happen if it heats up again, all that solid once again gets vaporized and enters the chamber and the vacuum gets degraded. So in this case, in the case of a cryo pump, it is not throwing the air outside. It is keeping it within itself. Only thing is it is collecting all the air constituent gases inside it and keeping it. So that's why, and then the vacuum improves very nicely. This is particularly required for water vapor. If there is water vapor is a main issue, then cryo pump has to be used so that because it very efficiently pumps the water. So for this reason, normally in any vacuum chamber, the pumping is first done with a roots rotary pump to get a -3 vacuum. Then only we switch over to the high vacuum, so that from -3 to -6, we use these turbo pumps and cryo pumps and many other varieties. So this is a brief introduction about the vacuum pumping. Of course, there are also gauges are there, valves are there. Vacuum technology is a subject which you should know later. Okay, I'll quickly skip it because already we have discussed different. Basically, there are three types of film growth. When the atoms come and sit on a substrate, it is island growth, means there are small islands are formed, and slowly these islands grow bigger and then they coalesce together and form a film. That is one way of film. Another is layer by layer. It's called Frank van der Meer method of procedure. where like ALD and MBE techniques, in that case, this is the layer by layer growth happens. First one layer, only after one layer is fully complete, the next layer will form like that. And in the other cases, is a combination. First layer will form. After a few layers, then again islands will start forming. This is a combination of a layer plus island. So this is called Stransky Krasnov type of growth. These are the three typical growth, thin film growth modes, when how the atoms come together, coalesce together, and film is formed. So depending on our type of application, we need to worry about what type of growth conditions are required to achieve that growth condition, what type of process parameters we have to control. So that is what is important here. So this is the various, first what will happen, they will condense and they will absorb and they will run around, atoms move around on the substrate. If the substrate is imparting some heat energy, then they will have freedom to move around. Normally, if there are certain defects, they get stuck at the defects. If there is a step on the substrate, or if there's a small crack or a scratch is there, first it will decorate all those locations nicely. These atoms get stuck there. Then the next round of atoms will come and get stuck to that place. So like that. So these are nucleation centers. The defects on the surface act like a nucleation center, or the dangling bonds if the surface is is activated by chemical etching, so that there are unsatisfied chemical bonds are there on the surface, then immediately the adhesion will be better. So these are some of the techniques that will have. So atomic layer engineering. So when these atoms come together, and there is always a first one or two atoms, three atoms, four atoms, as they come together, there is a combination of a free energy, thermodynamics little bit, the surface energy of the nucleus, and the volume energy. So only when the volume energy is more than the surface energy, it will become a stable thing. Otherwise, suppose minimum certain, so there is a critical radius of this nuclei. Till that radius is formed, it will not be stable. Means it will form, suppose 4-5 atoms come together, and if the energy, surface energy is more, they will again break up and they again come back, become atoms. So, but if the volume energy is good enough, if sufficient, suppose 10 atoms are come together in one shot, then the overall volume energy is better, then it will be a stable material. So that's this is what defines, controls the thermodynamics, only controls the atomic arrangement. Okay. Here, one very most popular picture I'm showing, this colored picture, where it tells the nature of microstructural nature of the thin film based on the conditions of vacuum conditions and deposition rate, substrate temperature. These are the things that will control the microstructural evolution of the thin film. Okay, so if we do deposit very fast at low temperatures, we'll end up with this very columnar along, very loose type of grain growth, which will not be stable. It will not adhere properly. Ultimately, what we want is whenever we are depositing film, we need a very strongly adhering. It may be a single crystal, suppose we want. In that case, we need to use low deposition rates and appropriate high substrate temperatures, so that appropriate energy is imparted to the atoms to move around and hold. If the temperature is too high, also is a problem, then it will again re-vaporize. So this diagram tells us what are the typical conditions are required to obtain either a crystalline film or amorphous film or an intermediate microcrystalline film. All that. So this you can study later when you take thin films as a subject. Okay, there are different methods. Already we had discussed most of these things. Thermal evaporation and sputtering techniques. In the case of thermal evaporation, as I mentioned, in this case, I'm showing an electron beam. It is, you see it is coming in the form, bending in the form of an arc that can be achieved by using magnetic field. There will be a magnet, high power magnet. And we know that charged particles bend in the form, when there is a magnetic field. So using that magnetic field, the charged electrons that are thermionically generated by heating a tungsten filament, they are and they are also accelerated by using high voltage. So those high voltage accelerated electrons, they bend through the magnetic field in the form of an arc, and they get focused onto the material that we want to deposit in the crucible, in a crucible. Okay, in that crucible, the high melting point material is put, And when this high energy beam is focused on it, energy is imparted and it will melt and then vaporize further. And then the vapor atoms come up to the top. And this is a general typical substrate arrangement. This is called planetary motion. There is one big holder will be there, which will be rotating. To that, smaller holders are put, which will be also rotating in our opposite direction. So this is all required to ensure uniformity of the film on the substrate. So for that reason, only all these arrangements are done. Otherwise, a simple one stable substrate also will do the job. Also, there are other issues because you see the vapor, the way it is going, the flux of atoms will be different at different locations. If we really want a uniformity over a large area, then we need to have appropriate uniformity masks we have to put so that the deposition rate, flux rate is uniform everywhere, so that the thickness is uniform everywhere. In certain applications, there is a requirement. And then there is a how do we know how much we are depositing thickness, what thickness we are achieving, what is the deposition rate? To know all that, there is a crystal monitor is used, and also there is another optical method of monitoring also. Here I am showing certain sources here. Here for thermal evaporation, we use molybdenum evaporation boards. And on the other side, I'm showing this electron beam deposition system. Here we see the beam hearth is there. In that the material is put. And then you can see the power supply. Power supply is there. High voltage is coming through these two leads. There is a tungsten filament here, which is heated, as well as the electrons are accelerated. And there is also a hidden magnetic field, which is not shown here. It is covered. So that magnetic field bends the beam and heats the material. And this is the deposition crystal monitor, which is there here, which can measure the thickness of the thickness that is getting deposited. Of course, that principle is based on shift in the resonance frequency of the crystal because of the because of the small mild pressure that is applied by the vapor on the surface of the crystal. There is a small shift in the frequency. That shift in frequency is measured and calibrated against the thickness. Of course, for that you should know the density of the material. You should know the atomic weight and density of the material, because it is dependent on that also. So that is all. Okay. Now, in the same, this is also ion assist deposition. I'll quickly go through it. It's basically the same as electron beam deposition. Only thing is, as I told, that to improve the process, we can impart extra energy by putting ion source. Here, what happens is the purpose of the ion assist gun is, as is shown in the earlier growth modes. Suppose island growth is happening. If there is no ion gun, it will simply grow island growth, and is a very, very rough surface. The surface will have very rough, and also a lot of porosity will be there. It will not be good. So to convert iron growth process into a layer process, what we can do, use the ion source, give some extra energy, or what you do is the growth, the islands are broken away, intentionally broken into, so that the atoms again vaporize and again once again get rearranged in a proper way to form a layer. So ion assist gun basically re-etches the film. It's a growing film, but it is etched by this ion gun partially, so that all the high point islands are etched, so that it becomes smooth. And then the atoms from the are once again rearranged. You are giving certain energy to the atoms to get themselves rearranged, so that the film is growing in a much more smoother way. So ion assist deposited films are much more smoother. They are much more density wise. They are more better, less porous. There will be less porosity. There will be no gaps. So ion assist is one of the standard methods of optical coating for this particular reason. And sputter deposition, I already told how it happens. There is a magnetron sputtering here. Here magnets are helping the ionization of the both atoms as well as the argon ions to improve the sputtering yield. Basically, sputtering yield has to be improved. For that reason, magnetrons are put. And typically the distances between the substrate and a sputtering target target and substrate. In the case of sputtering systems, it's maximum about 50 millimeters, 5 to 10 centimeters. That is the maximum gap, because the sputtering is happening very slowly and very slow yield. We cannot keep the substrate too far away. Whereas in the case of electron beam gun and ion assist, it is almost more than 30, 40 centimeters distance will be there. Sometimes 500 centimeters also. And the distance between the source and the substrate, that is much higher. But those are all a line of sight, because means the atom that is released by the source, it has to try, it will travel in straight lines unless it is knocked by the some other vacuum molecule, atmospheric molecule. Otherwise, it will move straight up and get deposited, hit the substrate. That's just a line of sight, what it's called. Okay, you tell me whenever the time is there. I'm just okay. So these are the different methods. And I just want to quickly go through. I already told about pulse laser deposition. The laser plume is generated by a laser beam, and it vaporizes locally. It will vaporize, maybe within a few centimeters, 2 mm or 3 mm or maximum 5 mm area is attacked by this laser, whatever is the spot size of the laser. From that area only material is evaporated, and it comes in the form of a plume and gets deposited. So for that reason, you need to continuously keep rotating the target, move the target, so that every time some fresh surface is coming into picture. Otherwise, it will simply drill a hole. That is not as. Here, I already talked about how plasma can improve the coating, how it can impart energy to the atoms so that they can form a better film. Okay. In the case of ion beam sputtering, this also I already explained. There is a target, the ions, and there is an ion source, particularly mostly argon is used, and high energy argons, they are ionized inside a chamber. Plasma is created inside the ion source and then accelerated through a grid and comes out with about 500 to 1000 electron volts energy. Those energetic argon ions, they hit the target and knock off the atoms. These atoms come out in the form of molecules and atoms, and they in the form of vapor and gets deposited. And in this case also, in case actually this itself gives a very good film as it is, as good as ion assist. But to further improve the process, sometimes another ion source is used to help in the assist, to have very, very smooth films with a very good very low micro roughness, so that the interface is very well defined for that purpose. But generally, only in special applications you require one more assist gun. Then two ion sources will be there. One for etching the target, removing the material, and there is for this thing. Okay. Now I come to the general thin film. Now I come to the optical coatings. So the process methods are same. So good addition to the substrate. These are all the requirements. It should be abrasion resistant. It should be producible, reproducible film properties, environmentally stable. All these things are required for any multi-layer. Optical coatings are multi-layer films. And this is also I already mentioned, so I'll quickly go through it. Surface cleanliness is very important. Lattice matching is important if you want single crystals. Substrate temperature is also very important parameter to have the good adhesion and good microstructure. The deposition rate, deposition rate means how many atoms are arriving and getting deposited on the substrate. If it is a very fast deposition, it will be highly porous. So chemical stoichiometry, already we mentioned all that. And in the case of ion beam assistance, ion assist, the ion beam parameters are, they dictate the terms in terms of how the film is grown. So these are the various aspects, and all these aspects are already covered. And I already mentioned substrate cleanliness is very important. That is normally done by etching and cleaning with soap solution, and then etching with chemically if required to have a good surface preparation. Sometimes in situ possible. In situ means after loading the substrate inside the chamber, getting the vacuum, you create a glow discharge plasma, create a plasma, and these ions, argon ions, hit the, no, without, there is no coating. it will simply knock the surface uniformly, so that any contamination is there on the surface is removed. This is something similar to that assist gun is there, no? I said ion assist, ion source. The same thing without depositing the film, if you are simply doing ion assist, simply cleaning the substrate, that is one way of preparing the substrate ready for the coating. Okay, so these are the methods. Now we'll come to the thin films thing. There are variety of optical films are made, high reflectance coatings on mirrors, and dielectric mirrors for lasers, for different types of 1064, 1532. These are lasers. Anti-reflection coatings and on the lens elements, as I already told, all cameras lenses, they should have an anti-reflection coating, whether it is a IR, if it is a IR imaging camera, night vision camera, in that case also we require anti-reflection coating on generally germanium and zinc selenide materials are used for these camera lenses. So these lenses after the fabrication, we need to put anti-reflection coatings. And in the case of NUV also, means we can use fused silica or sapphire. Okay. Yeah. Okay. So I'll quickly go through. Actually, I have not come to the main aspect of it. But anyway, these are the variety of filters that are possible. And these are the different chambers that we use. This is a very large area coating chamber. This is a medium size. This is a small size. These are all there in our LEOS lab at ISRO. We have used all of them. For example, these are used for simple coatings. This is for filters. This is for large mirrors. And in a summary, the different types of coatings and which is good for what application is mentioned here. So we have to characterize by using macrostructure calculation, by electron microscopy, XRD, and all that different methods. And all the optical properties, dielectric, electric properties have to be characterized depending on the application. So already this I have covered. Generally, typically the reflective coatings are done with aluminum, silver, gold, and chromium. These are the materials that are used for reflective coatings. Dielectric coatings are silicon dioxide is a low index material. Titanium oxide is a high index material. Tantalum oxide is also high index material. Generally, most of these filters and they are all done with multi-layer high and low refractive index coatings. And by appropriate optical design of the coatings, they are realized. So there are several aspects to it. I don't want to go through all this. This is in the case of optical coating, what you have to understand is these two things only: quarter wave optical thickness, half wave optical thickness. Means for a particular wavelength, and the optical thickness is refractive index and the physical thickness. The combination of the refractive index of the material and the physical thickness, the total is called optical thickness, the multiplication factor. Whenever that is a quarter, 1/4 of the wavelength, then it is called a quarter wave optical thickness. When it is a half the wavelength, it's called half wave optical thickness. So whenever there's a quarter wave optical thickness is there, then the phase difference is 90 degrees. So there will be a destructive interference. When it is a half wave optical thickness, the phase difference will be between the two rays, which are one is reflected from the top layer, another is from the next layer. So the two light waves reflected from these two locations, the phase difference, that makes there will be interference between those two waves. If the phase difference is pi or 2 pi, it will be constructive. If it is a pi by 2, it will be destructive. So basically, these optical interference techniques are used to design the films. And I'll quickly go through. This is one of a very broad band anti-reflection coating covering from 400 to 1100 nanometers NIR. This is a broadband optical filter covering only the visible part is transmitted. Rest of the light is cut off. This is done with the multi-layers of several layers, maybe 40 layers of high and low index SiO2, TiO2 combinations. As per the design, the thicknesses are to be controlled. And these are other filters. Filters means in any particular wavelength, center wavelength, we need a very steep cutoff on both sides. So these are all done with optical design software, which are available nowadays. So once these are the higher end of the technology of optical coatings. I don't want to get into it right now. Similarly, on the, I already told ARC, we have achieved anti-reflection coating of more than 95% transmission and very low reflectance on germanium and ginseng light for one of our projects. So now I'll conclude quickly. So there are different, to enable thin film processing, we need a very good vacuum generation, fabrication, good coating chambers are required, good control, industrial automation is required, good, and DCRF power supplies of very high quality and stability are required, and high purity coating materials are required, and good quality sputtering targets, rotatable multi-crucible electron beam evaporators, and thickness monitors, optical thickness monitors, and plasma assist innovations in plasma process technologies. Yeah, as you see, when I read out these things, you see that most of these things are not available in the country. I mean, we have to import all these things of very high, but I think it's high time that we need to get a good power supply, stable coating materials, stable targets. And of course, vacuum part, we are very good, vacuum. But then we are all importing the pumps and everything. Only the mechanical fabrication part, we have mastered that. To that extent, we are doing well. But it's still a long way to go to have indigenous coating chambers made within the country. There are some efforts are going on, but let us see how it works. So we need to, so thin film coatings is not an easy process, as I explained. Everything has to be very well controlled, and everything has to happen as per the plan, as per a design. Then only we'll get ultimate result. So it is a very tough process overall. So in summary, thin film processing materials is an enabling technology to develop advanced sensors, electronics, optics, and optical instruments. Thin film technology over the years has evolved from a very black art means we don't know, we simply deposit, we don't know what we are getting. That is the kind of thing some 50, 60 years back. But now it is a highly sophisticated deterministic production process because of the improvements in vacuum technology, because of improvements in computer-based automation of the processes, and in situ characterization methods like thickness monitoring, optical monitoring, and because of the availability of high purity chemicals. Because of all these conditions, the process has become much more reliable, highly reliable process. So further technology developments is possible, and it will happen. Now AML is very, everybody is talking about artificial intelligence and machine learning processes. Now that we physically understand the whole physics and chemistry and what all is happening inside the chamber, under what conditions, what type of film we'll get, everything is very well understood. All that knowledge has to be put in a computer as a artificial intelligence and machine learning, and then you simply load the material, load the substrate, apply these methods, run the program. We should get what we want. What the results should come out quickly without much effort. That type of thing over a period, I think the technology will come. So with the, now that we are having micro processing IC technologies coming within the country, photonic systems and devices are also, solar cells, a big impetus is there, and we need to develop the semiconductor policies there. So the future is very bright within the country itself, no need to go outside. So all you people, my students, my suggestion is you take up thin film process technology, thin film technology as a subject, learn and do well and contribute to the development of the country in all possible ways. Okay, with that I stop. Thank you.
Thank you, sir, for taking your time out and addressing all of us. It was such an informational talk. With your permission, if the audience have any doubts, they can come up.
Okay. Any doubts?
Okay, sir, I think there are no doubts. So
Okay.
I also thank our management for conducting such a wonderful webinar, which has given us so much of information.
Right.
I think we can conclude this session, sir. We'll end it with prayers.
Thank you. Thank you very much.
Thank you, sir.
Yeah.
Thank you, sir. Om Shanti Shanti Shanti. Thank you, sir.